Okay, let's get started. So I don't have too much more to say in the linear algebra unit. I just want to touch on sparse matrix storage and computation, and then I'll say a few more words, and then we'll switch over to the simulation unit. Okay, so I said last time as we were closing out that in R and essentially any of these other languages that you might use for computation, that there are generally going to be add-on packages or built-in functionality for working both storing and computing with sparse matrices, and that's generally going to be the way you want to go if you do actually have a sparse matrix. And so you might just have an arbitrary sparse matrix where some large percentage of the entries are zeros, 80%, 90%, 99%, 99.9%. Or you might have something in a very structured format like a matrix that's formed of blocks and then everywhere else is zeros, or a banded matrix where you've got only the non-zeros are only along sort of diagonals of the matrix. I guess maybe usually this way for you guys facing me. So if you know that you have that sort of matrix, you want to look into computations that can exploit that. And we've talked about LAPACK and the BLAS, which are the basic sort of core computational engines and codes for doing linear algebra calculations, and about making sure that you're using an optimized BLAS is usually a good thing to do if you're doing a lot of heavy computation. So I don't think I want to say too much more about that. Let me say a little bit about sparsity and just give you a sense for how arbitrary sparse matrices are stored on a computer and what the algorithms might look like in a pretty simple case. So there are a few different ways of storing a sparse matrix. So the idea is, okay, I'm going to start with some sparse matrix. Here I've just made the non-zero entries increasing just to sort of make them stand out, although I guess having all these zeros in here doesn't help very much. And so the question is, how do we encode this thing in a way that removes the zeros but preserves what the entries, the non-zero entries are, and gives us the necessary information to figure out where they are and work with them in an efficient manner? So there are a bunch of different formats. One of the common ones is called compressed sparse row. And basically the idea is you're going to work your way across row-wise of the matrix. You're only going to store the non-zeros. And then you're basically going to store three vectors. One vector is going to be the entries that are the non-zeros. Another vector is going to be which column is that particular non-zero in. And then another vector is going to be within the vector of values, at what point does each of the rows start? So if we did that for this one, we would have the values being 1, 10, 100, 1,000. So those would be the values. And then the columns would be 3, 5, 4, 1. And then what's often called the row pointer vector would basically be the first row, the first entry that's in the first row is this first element, so that's going to be a 1. And then the first entry that's in the second row is actually the third non-zero element, so that's going to be a 3. And then this is a little bit trickier because there are no zeros in the third row, and so I think the general way this gets done is this would be a 4, even though the fourth entry doesn't appear until here. So for the third row, you would go to look for in order to find the value in the third row, you'd go to look for the fourth entry in the values vector, but there is nothing there. And so the 4 is again repeated for this row, because the first non-zero element of this row is the fourth entry in the non-zero values guy. And then so on and so forth, depending on if the matrix continued. So that's the basic idea. And if you actually look at the if one uses the spam package in R, which is good for sort of arbitrary sparse matrices, and particularly if you're doing Cholesky decompositions with them. I'm on the wrong file here. We can look at that in R and see what happens. So what I'm going to do is I'm just going to make the matrix in full form as a dense matrix, which if it's a really big matrix, you would have some problems with first making the dense matrix and then converting it to a sparse matrix. But in this case, we can obviously do that. Now I'm going to convert it to the spam format for sparse matrices. And this is an S4 object-oriented framework for dealing with matrices. So we're going to have to use the @ symbol to get the slots of the of the object. I just realized as I was playing around with this morning, I can do it. I always forget what the function is that will tell me what the names of the slots are in an S4 object. But if we just do tab complete here, it'll actually just tell us what the possible slots are that we might be interested in. So that's a nice way to do that. So I can look at the entries. And this matrix is the same one that I filled in here on the board. We can see the entries correspond to what I was calling the values here. And the row pointers are indeed 1, 3, 4, 4, 5, and the column indices should be equivalent to what I'd given you. So that is actually the format that the spam package uses from within R. Any questions about that? Yeah, yeah. I mean, there are lots of different formats. I guess in this particular way, being versus some other format, or Y by row versus by column, or.
Yeah, why don't you just record the number of rows of each element?
So you could record, for example, the row and the column of each element.
Yeah,
That's a good question. I presume that people have thought about this and realized that if you store it in this way, that eases the computational burden. But you're right. Maybe it's a little bit more opaque than if we had just stored, say, the rows and the columns. I don't know if this will quite answer the question. I haven't really sort of thought about this carefully. But if we look at for example, how you would do a matrix vector multiply if you had a matrix stored in this sparse format, then the code, one version of the code for doing that would basically be loop over the rows. This presumes we've set up our answer vector x. We've already pre-allocated that. And then basically we're going to do a second loop that loops over this row pointer vector. Okay, so it's basically, it's looping over the values. Let's see. So it's looping over whatever's contained in here. So basically, this is going to allow us by looking at 1 and then 3 being the next one, we know we're going to grab out the first and the second elements from this column, and then the fact that it goes from 3 to 4 from the second to the third row means we're only going to grab out one element. So this for loop is basically looping over how many elements we need to grab out of each row. And then down here, all we need to know is what's the column index that corresponds to that non-zero entry, because that's the value of the B vector that we're multiplying into that we need to pull out and do the multiplication against. So yeah, it'd be interesting. You could think about like rewriting this for, say, the kind of format that you're thinking of, and see if there's some advantage to doing it this way versus the alternative way. So a partial answer, I guess. Other questions? And if you look, if you work your way through this, you can see that you'll save quite a bit of computation by doing it this way, as opposed to doing the dense matrix vector multiplier or analogous calculations for other calculations that we want to do. I don't think I'm going to say anything about this in particular, but like I said, there is this idea of banded matrices, and you can often do things quite quickly with banded matrices. One place that banded matrices come up is in time series. For example, if you have a moving average model, you end up with banded matrices. Just to make a few comments, this idea of a low rank update sort of goes back to this idea that I was talking about in class last time, which is whenever you're doing these computations, the way that I tend to think about this is we want to sort of combine some mathematical reasoning with being smart about the computation. So we don't need to be geniuses in terms of math and coming up with really smart approximations and really complicated calculations. On the other hand, we want to do enough math to ease the computation and be smart about it. And so one of the sort of principles I have in my head when I'm sort of starting to think about how do I do a calculation is the matrix that I'm working with, do I know something about constituent pieces that were used to form that matrix? And so examples that we've already seen are, if I'm doing least squares, I know that it's not just that I have some matrix in here, it's that I have a matrix and I know it was formed by doing X transpose X, so I can do a QR decomposition and do smart calculations based on that. We saw with the householder transformations that if we wanted to do something like this matrix vector multiply, and I know that the Q matrix was the householder transformation matrix where it looked, I think, something like this. Well, if I want to do Q times X, it makes a lot more sense in this case not to form Q and then do the full matrix vector multiply on X, but to recognize that, well, if this is Q, this is just going to be, Qx is just going to be this times X. Well, that's just X minus 2 U transpose X. This is just an inner product of a vector and a vector, so that's an order n calculation. The result of that is a scalar, which is just multiplied by a vector, so that's again an order of n calculation. And then I'm just subtracting a vector from a vector. So this is going to be an order n calculation, whereas this would be an order n squared calculation. So you just want to sort of think about where are your quantities coming from, and can I be smart about working with them? And that's sort of the same idea here. There's this idea of doing low rank updates to a matrix. So here I'm taking a matrix that has some rank, maybe it's full rank, and I'm subtracting off just the outer product of a vector and some other vector. So that's a rank 1 matrix, even though it's a full, say, n by n matrix. And so if, for example, I need to define the inverse of that resulting matrix, there's a formula that tells us how to do it. And that formula actually allows us to do it in a much more computationally efficient manner than if I didn't recognize the fact that this was a rank 1 update. So I don't really want to spend any time on this. If you're interested in this, you can take a look at it. But I sort of put this in here to just make you aware of this idea of inverses of low rank updates, and just to sort of reiterate this idea that if you know about the pieces of the matrix, you can often do faster computations. Okay, so there's this last section in section 6 that I don't think I'm going to go over now. So the idea basically is sometimes you may want to solve a linear system and it's just too big to do exactly with the sort of, what word am I looking for? With the techniques that we've already discussed. And there are actually iterative algorithms that will allow you to, for example, solve systems of equations. One of these is called Gauss-Seidel. We're actually going to see Gauss-Seidel in the optimization unit, so I'm gonna skip over that here. But basically, the idea is instead of trying to solve the whole system equation at once, you're trying to find this vector x, and the basic idea is you start with some initial vector x, and then you try and tune each of the successive elements of x and get closer to the final solution, and you work in an iterative fashion. And there's also something called the conjugate gradient method that converts solving this linear system into solving this optimization problem where f of x is the objective function. So we won't talk about this now. We might come back to it in the optimization unit, but the idea is that we're basically going to convert to an optimization problem, and then then it sort of uses some of the ideas that we'll see in the optimization unit about we're in this space, we're trying to search for a minimum. How do we choose what direction to travel in and how far to go as we try and walk our way through this space and try and find the minimum? So there are ideas related to that here with the conjugate gradient approach. Okay, so any final questions on the linear algebra stuff before I switch over to simulation? Okay. So the idea of simulation is we've already sort of talked in section this week about what is a simulation study, sort of what are the goals of a simulation study, what are some of the principles you might use if you're setting up your own simulation study, or if you're evaluating somebody else's simulation study. So we're not really going to talk too much about that here, since we've already talked about it in section. But we are going to do is talk in some detail about the Monte Carlo method for computing integrals and therefore for doing simulations. And we're going to talk about how do we generate random numbers on a computer and how do we make sure we're doing a good job of generating random numbers on a computer. And we're also going to talk about some methods for simulating values from distributions that are hard to simulate from. So those are some of the basic things we're going to talk about in this unit. Okay, so we've already sort of discussed this idea that the simulation study is often designed to see sort of, you have some statistical method that either you want to apply to a given data set or that you as a methodologist have developed this new methodology. And you want to evaluate the method and see how well it performs. You might want to see, like we saw in the section about type 1 and type 2 error. You might want to see about prediction error when you hold out data and see how well you do in terms of predicting on held out data. So you might be interested in a prediction problem. You might be interested in the coverage of confidence intervals or of Bayesian credible intervals for some particular method. So the idea is we can't repeat the real world in reality, but we can simulate the real world on a computer and come up with multiple data sets and actually put in practice the idea of repeated experiments and see how well our method does. So that's the sort of big picture. We might also be interested in comparing across different methods and seeing how well they perform. So we might design a simulation study where we're sort of competing different methods against each other. Okay, so we need to talk about Monte Carlo estimates of integrals. And the reason is that generally when we're doing a simulation study, somewhere under the hood, we're actually trying to approximate an integral. So we're trying to approximate usually some expected value. So that could actually be we're trying to approximate the bias of a method. So that would be an expected value minus the true value. Or we're trying to estimate the variance of an estimator. So that would be an expected value of some quantity squared. Or we're trying to estimate the coverage of a confidence interval. Well, that's the expected value of an indicator function that says, did we or did we not cover the actual true value with our interval? So a lot of these things are written in the form of integrals. And the idea is that we can't, in general, calculate those integrals in closed form. It's just too hard an integral to do mathematically. Okay, so we're going to do it by simulation techniques. Okay, so that was maybe a little bit vague, so let's be a little bit more concrete. I'm going to apologize for the notation here, because I think as I was looking at this the last day or two, I realized I probably should have switched up notation a little bit here. But hopefully this won't be too bad. I'm going to call Z our design matrix in a regression, and write out the regression equation as y equals z beta plus epsilon for some n by p matrix Z. And the reason is that I have this notation here where I'm using x for the random variable, so I don't want to use it for the design matrix here, but the notation's a little bit awkward, so I apologize for that. Okay, so suppose we decide, well, we have some data set that is coming to us, and we want to analyze that data set, but we're not actually all that sure about the assumptions of using the usual ordinary least squares model to fit the data. So one thing that we might do is we might try and simulate data under various departures from the linear regression assumptions, and then see how well does just using straightforward linear regression perform on data that are not quite satisfying the assumptions. So this would be us sort of as applied statisticians or scientists trying to say, I don't have a great sense of whether I should use least squares in this context, but let me do some simulations and see if I can justify using least squares. Or if it looks pretty bad, then I'd probably have to go think about a more sophisticated technique to use rather than using least squares. So that's sort of one way that this might come up. So I can think about, to try and sort of write this in notation here, I'm going to say, okay, the x over there is my random variable, so the data here are going to be y. And depending on whether you think about z as being fixed or sort of being generated in some random way, you might think about z as part of the data as well. I guess this is sort of a confusing way to write it. Let me write it as, I could write the data as being y, or I could write it as being z and epsilon jointly. So what do I have here? Well, I have, if you give me a data set, if the world gives me a data set, then what do I have? I'm going to come up with some estimator, the least squares estimator, that's beta hat of my data x. Okay, you give me a data set, I have some recipe, we call it least squares, but it's just some black box or some recipe that converts the data into an estimate beta hat, and the goal is that that beta hat is a good approximation of the underlying true regression parameters or coefficients, the betas. Okay, so the question is, I want to evaluate this relative to the true value of beta. Well, so I might be interested in a few different things that we're going to write out as expectations, and therefore they're intervals, and that's why I'm sort of going through this in sort of gory detail. I might be interested in the expected value of beta hat minus the true value of beta. So that would be something about, is my method biased for data generated in the kind of way that the data are being generated in? Or I might be interested in the variance of beta hat of x. So of course that's just going to be an expected value. Okay. Or I might be interested in whether or not in the performance of kind of a confidence interval for beta hat. So I might be interested in the coverage probabilities for beta hat of x plus or minus twice some standard error, some estimated standard error for beta hat. And that standard error is also going to be estimated from the data. So again, it's just the standard error is some recipe for taking a data set and converting it into this thing we call a standard error. So we can think of it as just being a function of the data set. So I might be interested in another expectation, which is the expected value of the indicator function that beta hat of x minus twice the standard error hat of x, that the true value falls in my confidence interval. Okay, so an expected value of an indicator function, this indicator function just says yes if this is true, no if it's false. Expected value of an indicator function is just a probability. So what have I done here? I've said, okay, I have these quantities that I might be interested in. They're all just expectations. So what I'm really interested in doing is calculating an integral here. And that's the challenge in this particular problem. If I could take my least squares estimator and actually just calculate these integrals mathematically, analytically, I'd go ahead and do that. I wouldn't need to do a simulation study. But in general, it's going to be, and if we assume that the epsilons are homoscedastic and that this is linear, then okay, yeah, we can go ahead and compute those quantities in closed form. For more complicated methods, we can't do those integrals. And as the data generating mechanism changes, we may not be able to do those integrals in closed form. So the idea is to do the simulation study. Okay, so the idea is, I'm now going to go back to a little bit more abstract notation and say we're trying to estimate some quantity mu, and that's some expected value under some data generating mechanism, f, for some function h of the data set x. So h is any of these functions that I have here. And x is the random data set, and that's generated from some distribution. Okay, so I don't necessarily know what this is. I may come up with some plausible idea of what this is and use that to generate data for my simulation study. Okay. Okay, so what is the idea of doing a Monte Carlo estimate? Okay, so the idea is I want to compute mu. I can't do that in closed form. So instead of actually calculating mu, which was that integral on the previous slide that I don't think that I can't do in closed form up here, the idea is I'm going to take mu hat to be this average. So what is this? This is basically, I'm going to generate a simulated data set. That's going to be x sub I. So this could be a vector of data. It could be a whole matrix of data. It could be any sort of form of data that I have. I'm going to take my functional h that converts the data to the quantity I'm interested in. And then I'm just going to average that over m different simulated data sets. Okay, so just like what was happening in the paper that we talked about on Monday. Well, by the law of large numbers, this converges almost surely as long as I generate these x's independently of each other, although it holds in more generality as well. But the simple case is we're going to generate these x's to be independent data sets one from another. And this is just going to converge to the expected value of h of x. So that's basically the justification for Monte Carlo methods. And this is this is sort of the most straightforward statistics problem that we generally see. We know what the variance is of this. This is just going to be some sigma squared, some variance, which is the variance of h of x, divided by the number of in this case, data sets, the number of samples that we have. Right? So this is just the usual variance of a mean. Except in this case, we're not talking about sort of statistical uncertainty or uncertainty from having from data. We're talking about the variance we're talking about is the fact that we are only generating m data sets instead of having an infinite number of data sets. So unlike in real-world applications, we can actually control this simulation variance by just increasing the number n, the number of simulated data sets we generate. So the only constraint, which we talked about on Monday, is how long does it take us to do the computations to do the simulation study. But if we do this and we say, oh, we're trying to estimate this mu hat, I might come up with an empirical estimate of what the simulation uncertainty is in my estimate of this. If I decide it's too big, I just go back to the computer and I keep generating more and more simulated data sets until I tamp down my uncertainty enough so that I'm satisfied I have a reasonable estimate. Okay, so let's think about how we would estimate simulation uncertainty. Well, we have that this is what the variance is, right? I'm just writing that down as the actual quantity. But we have our usual estimate, unbiased estimator of a variance. Well, that's just going to be 1 over n minus 1 to get unbiasedness of the sum of the h evaluated for the individual x's minus our estimate of mu squared. So if I now want to say what's my estimate of the variance of the simulation, of the variance of estimating from estimating mu with mu hat, well, that is now this quantity. So I'm just taking my original sigma squared over m, plugging in an estimator for sigma squared, and it becomes this. It becomes this sum of squares divided by 1 over m and m minus 1. So it gets a little bit confusing here because of the fact that we're plugging in this estimator and there end up being 2 m's in the denominator. But that's where the two m's are coming from. Okay, so any questions about that? Okay. I think the most confusing thing when I think about these things is there's this sigma squared that's the variance of h of x, but then there's this simulation variance, and that's a different variance, and they have different things in the denominator. One has m, and one has this order of m squared term in the denominator. Okay. So here's another example of this. Again, this is sort of a silly example, but suppose I'm used to using the mean, the actual sample mean of a distribution to estimate the population mean of a distribution. And somebody comes along and says, hey, I have this new estimator. It's take all of the values, order them, and take the middle run. Right? I'm going to call this thing the median. This is my new estimator. I think it might be a better estimator because I think it might have lower variance than using the mean, the actual sample mean, to estimate the population mean, because this new thing that we're calling the median is not subject to influence from outliers. So there is presumably no good way, I think this is true, I guess I don't know this for sure, to estimate the variance of the median as an estimator. So I would have to do that via a Monte Carlo estimate because I can't actually do the integral in closed form. So what do? Well, I generate a whole bunch of data sets, each xi. I calculate the median. I take the mean of all of those medians. And this gives me a Monte Carlo estimate of the variance of the median as an estimator of a population mean. The variance of a sample median as an estimator of a population mean. So what's the challenge at this point? Well, then we have to say, if we're setting up our simulation study, the same sort of challenges that we talked about on Monday. What is the data generating mechanism that I want to evaluate this new estimator, this median, with respect to? So they came up with different ways of generating data for, do we have 3 mixtures and how far apart are the means and how big are the variances and what are the weights, the alphas on the different components? They had to come up with all those terms that determine what the data generating mechanism is. We would have to do the same thing here. We'd have to say, under what distribution am I going to generate data to see how well to see under those circumstances how well the median does relative to the mean. And we'll never be able to answer the question completely because we can't generate data under all possible data generating scenarios. We can only generate them under some fixed set of them. Okay, so any questions about this? Okay, so there are some strategies when you're doing Monte Carlo sampling to reduce variance. I don't think this is, to me they don't come up enough that I don't think it's worth going into a lot of detail here, but I have a few examples here that you can take a look at. So let's move on and talk about random number generation, which we're going to spend some chunk of time on. So basically, on a computer, when we generate random numbers, they're not actually generated in a stochastic fashion. They're actually generated deterministically, but the goal is to generate them in such a way, since a computer is deterministic, it just computes what you tell it to compute. The idea is to generate numbers in a deterministic fashion that behave like they were generated randomly. So the whole goal is to come up with a recipe or a formula for doing this, such that the numbers that we get out, if we look at them, they look like they're essentially generated randomly, and then we can use them as if they were. So that's why random numbers on a computer are called pseudo-random numbers, because they're not really random. And the whole business is thinking about what are the properties of the different recipes that people have come up with. Okay, so stepping back a second, basically a random number from any distribution can basically be generated from a standard uniform distribution on the interval from 0 to 1. So the problem basically reduces down to how do I generate random uniforms between 0 and 1? And then there are lots of recipes for taking that and converting to a normal random variable, or to a gamma, or or to a categorical random variable for that matter. Okay, so basically what happens is a random number generator is basically a deterministic sequence of numbers. It's a finite set of those, and they basically repeat. So you can sort of think of a random number generator as you've got this big circle of numbers, and if you're generating random numbers here, the next random number is generated, and then the next one, and eventually if you generate enough random numbers, you're going to come back around and you're going to hit exactly the same number again, and so there's going to be this periodicity. Luckily, for most random number generators that are used in practice, this is really, 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 really long, so that you would essentially never come all the way back around. And when we talk about the seed of a random number generator, the seed basically just says, where are we in this cycle of random numbers? So if I had one seed and I set it and that put me here in this position, I might set the seed to a different value, and that might then put me over here. And so I then, say in 2 different simulation studies, I might be using these random numbers for the first part of the simulation study, and then in the second part I might be using these random numbers from down here in the cycle. Okay, so the question is, well, how do we actually figure out a recipe for doing this? So a standard way to do this is as follows. You have some initial set of numbers that I'm going to call u k minus 1. Or you have, let's say, this is basically a recipe for, suppose I have some numbers, how do I generate the next one? That's sort of how we're going to do this. You have some set of numbers, so going back sort of j values in the history. How do I generate the next one, the kth value? Well, I apply some function to these numbers, and then I divide by m and take the remainder. Okay, that's the recipe for generating these pseudo-random numbers. The idea is that if I take the remainder of some operation f, that the remainder often seems like it's sort of quasi-random. It just seems sort of like arbitrary digits. And so that the idea is to try and exploit that idea. And in order to get things between 0 and 1, well, if I'm dividing by m, then the biggest value I can get is going to be basically m. So I'm going to generate the UKs. I'm just going to keep marching along and generating the next one, the next one, and the next one. And then to actually have my standard uniforms, I'm going to divide each of those values by m. So that'll center it. That'll put it between 0 and 1. Okay. Any questions about that? Yeah.
So all the random number generators every computer the same, or something different?
Well, different software will use different algorithms for generating random numbers. A lot of the, if you go and look at what R does and what Python does and what MATLAB does, in a number of cases they overlap in terms of they might be using the same random number generator. So R, for example, the default one is something called the Mersenne twister that we'll talk about a little bit. And I forget if it's either Python or MATLAB, but one of the two of those uses the Mersenne twister also as its default. So there is some overlap here and some agreement on what are good random number generators and what are bad ones, and we'll talk a little bit about that. Other questions? Okay, so we'll do a little example of one of these sequential congruential generators. This one will just be a linear one, because what we're going to do is, instead of having some function f that's complicated, we're just going to multiply by a number a. That's going to be our function f, and then we're going to do the remainder from dividing by m. And this one is just going to use the previous value. It's not going to use the jth previous values. It's just going to use the actual previous one. So the idea is we choose our generator is developed by choosing an a and choosing an m, and then as long as we have a starting point, an initial u, then we can just start the process along and march along. You'll notice that if we do it in this fashion, the periodicity, the length of the number of unique values before I get back to the starting point, can't exceed m minus 1, because when I divide by m to get a remainder, there are only going to be that many unique values that I can get from doing a remainder when I'm working with integers here, which is what I'm working with here. So as an example of this, we'll just do a very simple one just to sort of get a feel for this. So suppose I choose a equals 7 and m equals 13. So in reality, if you use this method, you're going to choose numbers that are much larger than this. So this would be a very bad random number generator. But suppose we start out with u sub 0 equals 2. Well, my recipe is take 2 times 7, that's 14, divide by 13, and take the remainder. So that's going to be 1. So u sub 1 is going to be 1. 1 times 7, divide by 13, take the remainder, that's going to be 7. So that's u sub 2. U sub 3, 7 times 7 is 49, divide by 13, that should be 10. I'm just going to proceed. You can see there are only so many unique values I'm going to get, and so if I actually write this out, I'll get, what I would get is I'll get 10, then I'll get 5, 9, 13, 11, 12, 6, 3, 8, 4, 2. The whole point of writing this out was to see eventually I'll get the 2 back. And now I'm back here. This is a deterministic recipe. This 2 and this 2 are the same. When I repeat the recipe, I'm going to get 1 again. So this is the periodicity of I've traveled all the way around the circle in this case. So as you would guess, if I now divide each of these numbers by 13, I'm only going to have a limited number of unique values. This is not going to look like a particularly good random number generator. But if you set a and m to be larger, things start to look better. So here's an example where we're going to set a to be 171 and m to be 30,269. So these values have been carefully chosen by folks to try and come up with reasonable random number generators. And I'm just implementing my recipe here in R of doing a times u and then doing the remainder after dividing by m. Okay, so that'll generate some u's. I'm also going to generate some random uniforms just using whatever R's default is for generating random numbers. And then the idea is let's plot this and see what these things look like. Not sure why RStudio's, oh, that figure margin problem. Okay, so let me try it again. Okay, the aspect ratio is not particularly good here. That's a little bit better. So we can see, so these are the U's that I just generated with that particular recipe, and these are the U's that come from R, and so I'm just plotting them sequentially over iteration number, just to get some sense of does it seem like they're bouncing around in a random fashion. And we can see, they actually look pretty similar from the left to right. It's often really hard to evaluate random number generators. That looks perfect. Maybe that looks fine. Maybe this looks fine. I don't know. Does it seem weird that these seem sort of stable around here or here? Is that just chance variation, or is that some sign of some inadequacy in my random number generator? Or we can look at a histogram. This should be a standard uniform distribution, both of these, right? So part of the question is, well, is this just chance, or is that some indication of inadequacy in the random number generator? Well, this is with the recipe that we just implemented manually ourselves. If we look at what R's implementation is, and presumably it's a pretty good implementation, we see, there are lots of places, there's lots of variation here if we only sample 100 random values. And so we're not getting something that, we're not getting a histogram that's flat across just because of sampling variability. So those are the sorts of things that come up and that one starts to think about when one is trying to evaluate whether one has a good random number generator. And you can think about what are the properties that I would want to have from my generator. Well, I know that I want these things to be uniform on 0, 1. I also know that I want them to be independent from one iterate to the next. So I'd want to evaluate whether or not there seems to be some sort of time series type dependency over iterations. But I also want multivariate uniformity. So I want to make sure that if I think about a subset of, say, j of them, that subset lives in the j-dimensional random uniform distribution as well. That actually turns out to be one of the hard things to accomplish. And if you these linear congruential methods, like the one that we were just talking about multiplying by a and then doing the remainder of dividing by m, it turns out that if you look at sets of k samples, k sequential samples from using these linear congruential methods, they actually, and you look in this k-dimensional subspace, they actually you'll actually see a lot of structure in the samples, and so it turns out these linear congruential ones are not all that great as generators because of that. So they have some structure in the multivariate joint distributions. Okay, so it actually turns out that one nice step that you can take, there are some inadequacies in that simple generator, is actually to take 3 of these linear congruential generators and combine them together. That gives us something called Witchman-Hill, which is actually one of the generators that you can use in R. And Witchman-Hill is basically do the recipe that we've been talking about, multiply by a and divide by m, but do it with 3 different values of a and 3 different values of m. Okay, so the first value of a and the first value of m is the one I just showed you by example. And what is it? Well, you just have these 3 separate generators proceeding along, and then the way I generate the u is I take the x1 value and divide by its m, I take the y value, divide by its m, and I take the z value and divide by its m. So each of the x, y, and z sequences are the a times the u remainder after dividing by m, and then this is how I combine them, and I divide by 1 to get the remainder of that. And that gives me the Witchman-Hill generator. Questions about that? So we could actually do this in R, and I'm going to show you this so that we can get a better idea of what the seed is and what that means in these cases. So I'm actually going to set the random number generator in R to be Witchman-Hill, so I do it with this RNG kind syntax or function. I'm going to set the seed to 0, and I'm going to then, the seed is stored in this object called .random.seed, so I'm going to save that for the moment. And what am I going to do? Well, I'm going to generate 10 random numbers from R's default approach. And then I'm going to code up my own Witchman-Hill generator myself and do it manually. But the way that I'm going to do it is I'm going to start with the seed that I saved from R's random number seed. So it turns out the random number seed in R, the first number it's a vector. The first number determines what kind of generator I'm using. And then the remaining numbers are basically tell me where I am in this sequence in the cycle. Well, with Witchman-Hill, what we saw was that I basically have these 3 different generators. So what do I need to know about where I am in the sequence? Well, I basically need to know the x value, the y value, and the z value, and that tells me where I am. And so if I actually looked in R and looked at this, let's go ahead and look at save seed. So 400 means it's the Witchman-Hill, and then these are the values of the x, the y, and the z that tell me where I am. And so I'm going to use those values, and I'm going to manually do Witchman-Hill on my own. So I'm going to multiply by a, I'm doing it in a vectorized fashion here, and divide by m and get the remainder. And then I'm just going to proceed along and generate 10 values. And I'm going to, again, follow the recipe of dividing by 1, of summing them up, dividing by the n values, dividing by the n values, summing up, and then doing the remainder after I divide by 1, which was the recipe I showed you. And if I now look at and print out what's the random value that I got from R, that's in this vector U from R, and then the result of my manually implementing Witchman-Hill, what I see is that I can actually reproduce the exact random number generated myself. So I can really understand what's going on. And you'll see I'm getting precisely the same answer from here's R's random uniform function, but based on using Witchman-Hill, and here's my re-implementation of it. And the other thing I can do is I can now look at the 10th value in what I just generated. And if I look at the current value of the random seed in R, I'll see it's the exact same value. So I understand exactly what's going on with the seed in this particular case. It's just these x, y, and z values, and that's straightforward to work through. Okay, so any questions about that? Okay, so let me just skip ahead for a moment and say one thing briefly, and then we'll come back to the main Mersenne twister on Wednesday. So basically what happens when you set the seed in R, so we just saw in Witchman-Hill that the seed is actually these 3 numbers. It turns out with the Mersenne twister, the seed is actually 624 different integers. So when you set the seed in R, what you're doing is setting a single value. And what it does is it then has some recipe for then taking that single value and then creating the necessary actual seed values that are needed for the particular generator that you're using. So for example, with Witchman-Hill, there's some recipe that takes a single number, the seed you give R, and converts it into these 3 numbers, which is the seed that we've just seen with the Witchman-Hill example. And we've seen that that's stored in .random.seed. You can get help on some of the different random number generators in R by just doing help on RNG kind. And then I think the last thing I'll mention here is that in general, it's a really good idea to set the seed before you do any calculations in R that involve random numbers. And the reason is then you can come back and repeat exactly what you did before if you've set the seed. If you didn't set the seed and you do some calculations and you get some funny answer, you're not going to be able to go back and recreate what you did because you're not going to be able to generate those same random numbers again. Okay? So that although if you start up R again, it might be starting. I forget exactly how R chooses the seed when it starts up. It might be that you might be able to stop R and restart it and get the same thing back, but you're not necessarily going to be guaranteed to be able to do that. So let's quit there. I will talk about the actual Mersenne twister, which is the default, on Wednesday, and we'll talk about setting the seed and doing some more stuff in R as well.